Hello, my name is Yash Jagadi, and today I want to present my project SkyWindFarm, harnessing high-altitude wind power in a scalable manner. Wind power is primarily a function of the cube of velocity. Unlike traditional turbines, which increase power by enlarging the cross-sectional area, airborne wind energy systems, or AWEs, seek to leverage the cubic relationship with power by harnessing higher velocities to yield significantly more energy. The viable distribution, used to model wind at various locations, has proven over 99% accurate in predicting high-altitude wind behavior. Viable analysis indicates a significant increase in wind speeds at 3,000 meters, with speeds ranging from 18 to 33 meters per second for over 90% of the time, and a mean speed of 26.7 meters per second. Current R designs, though, struggle to harness high-altitude wind power scalably. While capable of generating power, they demand substantial real estate and are not designed to be farmable. Although they can produce power in the kilowatt range, these systems cannot reach the megawatt range required by the cities. Additionally, most AWEs operate at altitudes below 500 meters, making their power generation intermittent. Vertical axis wind turbines, or VAWTs, emerge as a particularly favorable technology over horizontal axis wind turbines for several reasons. VAWTs offer unique advantage in farm configurations, notably superior energy density and efficiency. Additionally, VAWTs offer the added benefit of achieving higher power coefficients, or CP, at lower tip speed ratios, or TSR, which is important in high wind speed environments, as higher TSR levels can introduce structural challenges and compromise system integrity. A SkyWind farm, as shown in this figure, is composed of one or more energy units, with each energy unit featuring a cluster of four counter-rotating VATs. The configuration of these energy units is flexible, allowing for optimal positioning in the airspace to maximize each energy unit's output. Designed for long-term autonomous operation at high altitudes, each energy unit in the SkyWind farm undergoes an initial towing phase to reach its designated operational altitude. Once airborne, the farm employs a dual lift strategy that combines both aerostatic and aerodynamic lift mechanisms. This feature allows the farm to maintain or adapt its altitude with high efficiency, optimizing its position relative to high-density wind layers. Upon attaining the desired altitude, the VAT clusters within each energy unit start converting the kinetic energy of the wind into electrical energy. This energy is then transferred to the ground through a specialized electricity conducting tether, facilitating immediate integration into the existing electrical grid. By dynamically altering the angle of attack of lift wings, the system can execute a controlled, gradual descent. The key innovation in SkyWindFarm is the VAT cluster, comprised of four three-plated counter-rotating H-rotor wind turbines made using carbon fiber and hydrophobic fabric composites. The choice of material ensures that the turbine operates at high wind speeds of up to 60 meters per second while only weighing 300 kilograms. A key challenge for traditional VATs is the negative torque during the airfoil's return revolution. SkyWindFarm addresses this with a diffuser-augmented arrangement that prevents air from hitting the blades at negative angles and accelerates air at positive angles, enhancing power output. Unlike crosswind systems, which frequently encounter significant tether tensions, SkyWind farm tether remains static. Furthermore, the SkyWind farm uses electrical conduction tether capable of transmitting electricity efficiently over long distances, proven in applications reaching 15 kilometers to transmit power. SkyWindFarm uses helium as lighter than air, or LTA gas, for lift. The LTA shell comprises of an outer layer of polyvinyl fluoride to serve as an environmental barrier, a polyester film acting as a helium barrier, and a woven polyester base cloth for tensile strength. The inner surface is coated with a thermoplastic urethane layer for effective heat sealing. The configuration allows the semi-rigid LTA shell to adapt to the varying pressure outside while also ensuring the helium is secure within, only needing to be refilled once every 2 years. The blowdown angle determined by the ratio of lift to drag arises from the drag faced by the farm, causing its airborne trajectory to follow a slight angle. A high blowdown angle necessitates longer tethers and consumes substantial space for operation. Scaven Farm has one of the lowest operational blowdown angles, around only 16 degrees of any AWES, thanks to its dual lift mechanism. SkyWindFarm integrates aerostatic and aerodynamic lift with helium and lift mechanisms, offering system stability and operational flexibility. The dual lift approach has an operational time of 97.5%, the highest uptime in any AW. In the very rare case where aerostatic lift is not enough, crosswind flight can help keep the system up in the air. To optimize VAT clusters, over 100 different VAT configurations were tested. The setup for these tests included a 26.7 meters per second velocity inlet and an atmospheric pressure outlet. The test simulated an operational altitude of 3 kilometers. The turbines employed no slip walls and no deformation, and had a rotating domain. The present SkyWind farm model features an innovative cluster of 4 watts per energy unit, as depicted in this figure. This design was optimized from over 100 different configurations, all tested on the Agate supercomputer cluster. To identify the most optimal configuration for the VAT cluster, simulated annealing was employed to get to this design. This current configuration aims to overcome some of the inherent challenges in VAWT performance while maximizing efficiency. During the simulation runs, the Y plus value for the mesh fell within the range of 1 to 5, and the mesh consisted of an average of over 3 million elements. Fluent code was employed to solve the unsteady Reynolds average Navier-Stokes equation using the finite volume method. The simple algorithm was utilized for semi-implicit method with second-order spatial discretization for pressure, momentum, turbulence equations. To capture the turbulence correctly, SST-K omega turbulence model was adapted. The best configuration found is shown here. The optimized VAT configuration had a peak performance at TSR of 3. In this VAT cluster, optimized from over 100 different computational configurations, the performance of each of the 4 turbines was significantly higher than a lone VAT itself, thanks to the specific turbine and diffuser wall arrangement. Before concluding on a design, multiple turbine models with various guide vane configurations and turbine configurations were also tested in the wind tunnel, along with computational tests to ensure accuracy. It was found out that 4 turbines offers the maximum performance per turbine while also being the most efficient in terms of mass per watt of power. A few of the previous models built and tested could be seen here. The final design was a 4-turbine VAT cluster as shown from the CFD section. The primary objective of the wind tunnel testing was to corroborate the CFD simulations concerning the aerodynamic behavior of the turbine cluster. To this end, a meticulously crafted lab-scale prototype modeled at 1:20 scale ratio was employed as depicted above. To ensure the accuracy of the test, the pi terms TSR and CP were utilized as they are scale independent. Wind tunnel testing was executed across TSRs ranging from 2 to 3.5 in increments of 0.25. The measurement phase shaded in peach captures the steady state operation where wind power stabilizes. It is during this phase that the most critical and relevant data for validating the CFD simulations are captured. With a correlation coefficient of over 0.95 between wind tunnel tests and CFD runs, the tests confirm CFD's accuracy and demonstrate turbine clusters efficiency as a leading awe design. The cumulative power output for a single energy unit in this configuration was determined by using the average CP of the physical testing and the CFD simulations, which is 0.43 at tip speed ratio of 3. Based on those models, the average power was calculated to be 157 kilowatts for an energy unit designed to operate at 3,000 meters with the average wind speed of 26.7 meters per second and atmospheric pressure of 0.8 kilogram per meter cube. Additionally, stability analysis was conducted to optimize the shape of the helium balloon design and proved that this design can reject a disturbance as abrupt as a sudden change in wind speed of 30 degrees while still maintaining a stable operation and facing the wind head-on. The simulation employed the fluent code to solve the unsteady Reynolds average Navier-Stokes equation using the finite volume method. The simple algorithm with SST-K omega turbulence model was adapted. Gradients were calculated using the least square cell-based algorithm. The stability analysis revealed that SkyWindFarm could reorient itself to face the new wind direction within a duration of only 7.2 seconds, as indicated above. This swift reorientation highlights the system's resilience and adaptability to sudden wind changes, vital for maintaining consistent energy generation and overall safety. I adapted NREL protocols for emerging renewable energy systems when projecting cost analysis. The analysis assumes an annual production of 250 energy units after an initial phase of 150 units. As the production increases, the cost of each energy unit is expected to decrease significantly. However, the goal here is to be conservative. Over 20 years, SkyWindFarm's total life cycle cost is calculated at $540,000, resulting in a levelized cost of energy of approximately $25 per megawatt hour. A principal factor underpinning the superior cost efficiency of SkyWindFarm relative to traditional energy sources is the reduced material consumption. The following figure drawn to scale shows the comparison between a conventional 150 kilowatt wind turbine and the SkyWindFarm configuration. In America's most rural regions, traditional wind energy harvesting is often unfeasible due to geographical constraints. These regions often must hence rely on power from non-renewable energy sources. To meet the climate goals of our nation, these areas require modular, clean, sustainable, and reliable power sources. SkyWindFarm stands out as a viable renewable energy solution for remote communities, promising affordability and efficiency where other renewables fall short. SkyWindFarm has now achieved TRL4 exceeding current designs by 25% in efficiency. SkyWindFarm can transition from powering small remote communities to multi-megawatt setups capable of supporting large communities, making it the first R design to be scalable. Further, SkyWindFarm is also the first R design that can function as a primary source of power, making it a promising solution for remote communities. Finally, the design for SkyWindFarm has been patented and is publication under Renewable Energy Journal. I hope to continue working on this project, and hopefully one day we can all see SkyWindFarm powering communities around the globe.